Welcome to our module on Python for Data, where we will explore how Python becomes an indispensable tool for data analysis. We will focus on the essential libraries that form the backbone of data science workflows in Python. First up, we have NUMPY, which stands for Numerical Python, a cornerstone for scientific computing. It provides the fundamental building blocks for high-performance numerical operations in Python, crucial for scientific computing. A key feature is its support for multidimensional arrays, which are incredibly versatile for various data types. The n-dimensional array, or NDArray, is NUMPY's core data structure, designed for efficient storage and operations on large datasets. NUMPY excels at vectorization, which is a powerful technique for speeding up computations significantly. Vectorization performs operations across entire arrays without needing explicit Python loops, making your code much faster. Another fantastic feature is broadcasting, which simplifies operations between arrays of different shapes. Broadcasting allows operations on arrays of varying sizes and shapes without explicit dimension matching, offering great flexibility. NUMPY also comes packed with a wide range of built-in mathematical and statistical functions. These functions provide high-level operations for common math and statistics tasks, making complex calculations straightforward. Lastly, NUMPY offers powerful indexing and slicing capabilities for accessing array elements. These mechanisms allow you to efficiently access and modify specific elements or subsets within your arrays. Now, let's dive into creating and operating on NUMPY arrays, which are fundamental skills for data manipulation. We will explore the essential array manipulations that you'll use constantly in your data science journey. Let's start by looking at how to create these powerful multidimensional arrays in NUMPY. NUMPY arrays can be easily created from Python lists or using functions like NP, zeros, and NP. Ones, the core is the NDArray. Here, we import NUMPY and create two arrays, a one-dimensional R1 and a two-dimensional R2 from Python lists. Next, we'll explore element-wise operations, which are incredibly efficient for performing calculations across arrays. NUMPY enables fast, element-wise operations like addition, utilizing vectorization to eliminate the need for slow explicit loops. This code demonstrates simple element-wise addition, where R1 and R2 are added together to produce a result array. Moving on, let's explore advanced array access and operations, which are crucial for manipulating complex datasets. These techniques provide efficient data subsetting and ensure shape compatibility, streamlining your data processing tasks. We will now look at how to use indexing and slicing to precisely select parts of your NUMPY arrays. NUMPY's advanced indexing and slicing allow you to access specific elements or subsets, offering greater power for multidimensional data than Python lists. This example shows how to access a single element and then extract a subarray using multidimensional slicing. Finally, let's revisit broadcasting, a powerful concept for performing operations on arrays of different shapes. Broadcasting enables element-wise operations on arrays of different shapes, provided they are compatible, avoiding the need for explicit reshaping. Here, we add a scalar value 10 to every element of the array R using broadcasting, demonstrating its convenience. Let's explore pandas, a true powerhouse in the world of data analysis, making complex tasks much simpler. Pandas excels at structured data manipulation, providing intuitive tools to efficiently organize and transform your datasets. First, we have DATA-FRMES, which are fundamental for handling tabular data, a core concept in pandas. DATA-FRMES are two-dimensional labeled structures, much like tables you'd see in databases or everyday spreadsheets. Next, let's look at series, another key data structure in pandas for working with one-dimensional data. A series is a one-dimensional labeled array, incredibly versatile and able to hold various data types. Pandas also provides robust capabilities for handling missing data, a common challenge in real-world datasets. It offers functions to efficiently identify, fill in, or completely remove any missing values from your data. Data indexing and selection are crucial, allowing you to pinpoint and extract specific parts of your dataset. With Pandas, you can easily access data using labels or employ more advanced indexing techniques for precision. Now, let's walk through a stepwise Pandas data workflow, understanding the journey from raw data to insights. This workflow guides us through the entire process, transforming raw, unprocessed data into valuable, actionable insights. Our first step is to grasp the fundamental concepts of series and DATAFRAMES, the building blocks of Pandas. This code demonstrates creating a series from a list and a DATAFRAME from a dictionary, showcasing basic Pandas object creation. Next, we learn how to load data into Pandas from different file formats and save our processed data back out. Here, we see how to read data from a CSV file into a DATAFRAME, and then save that DATAFRAME back to a CSV. An important step is accessing specific data points, either by their labels or by their numerical positions within the structure. This code illustrates accessing data using lock for label-based indexing and ilock for integer location-based indexing. We can also manipulate data by applying conditions, which helps us filter and transform our datasets effectively. This snippet shows filtering a DATAFRAME based on an age condition and creating a new column by adding to an existing one. Let's discuss managing data quality in Pandas, a crucial step for ensuring reliable analysis and accurate insights. This involves cleaning our datasets by addressing inconsistencies and summarizing them to reveal key characteristics. First, we need to check for any missing data, which is often represented by N or none values. Once identified, we can choose to fill these missing values using various strategies, like mean or median. Alternatively, if appropriate, we might decide to simply drop rows or columns that contain missing data. Finally, we can group our data and aggregate it to summarize information, like calculating averages or sums. Now, let's explore Matplotlib, a powerful and widely used library for visualizing data in Python. A line plot is excellent for showing trends over time or continuous data points, connecting them with lines. Bar plots are ideal for comparing categorical data, where the length of each bar represents a value. A scatter plot helps visualize the relationship between two numerical variables, showing individual data points. Histograms are used to display the distribution of a single numerical variable, showing frequency within bins. Lastly, a pie chart represents parts of a whole, showing proportions of different categories in a circular form. This slide brings us to a summary of what we've learned, highlighting the most important concepts from our session. Let's review the key takeaways, the essential points you should remember from our discussion today. First, remember that NUMPY is crucial for efficient multidimensional arrays and powerful mathematical functions in numerical computing. Pandas, on the other hand, gives us powerful data structures like series and DATAFRAMES for effective data analysis and manipulation. Matplotlib is your tool for creating versatile and customizable data visualizations, helping you present your insights clearly. Together, these three libraries, NUMPY, Pandas, and Matplotlib, form a foundational toolkit for all your data science workflows in Python. Therefore, mastering these libraries is absolutely crucial for efficient data handling, thorough analysis, and compelling visualization.